So good morning, everybody. In yesterday's session, we have started discussing about supervised learning algorithms. So what did we discuss within supervised learning algorithms? We have seen KNN algorithm, and we have also seen naive Bayes. And yesterday we have discussed regarding the theory of decision trees. Okay, we have seen how to do these two in RapidMiner Studio as well. We are about to see the decision tree. Before moving on to RapidMiner Studio, we will discuss about what is present in the mind map. So here we are currently in the stage model building, in which we are discussing about the supervised learning algorithms, which is also called as predictive modeling. So in predictive modeling, you have classification models, which I've told you the different types with examples. And coming to the second one, shallow machine learning models, in which you have naive Bayes, k nearest neighbors, and then divide and conquer, which is decision tree. So the current version of decision tree is C5.0, which I've told you yesterday. And coming to here, you have different types present. I've already talked about what is greedy algorithm and why we are calling this as divide and conquer, and how the tree structure is looking like, and what is entropy, what is information gain. We have seen all these things yesterday in yesterday's session. So what is this? The first one. The first one is regularization parameter is pruning. And tree structure consists of different nodes, that is root node, internal node, and leaf node. So based on recursive partitioning or divide and conquer method, we are using this decision tree. And if I want to choose one particular column or one particular attribute as a root node, which one it is to be, it will talk about with the help of information gain and entropy. What is entropy? Entropy is a form or it is a measure of impurity or error. And information gain, how will I get information gain? That is entropy before minus entropy after. So entropy after is again, we have to calculate entropy left and right, then we will get entropy after. And we have to choose the root node by selecting that variable with highest information gain. So this is what we have seen in decision tree theory. Now let's move on to the practical part, how to work on this using the tool RapidMiner Studio. So let me open our application. Just give it a moment. Okay, here's our application. Now let me open the blank process and show how to work on decision tree and what is the operator that we are going to use. Just give it a second. Here's my process. Now I want to show you the decision tree application or decision tree algorithm, how to work on it. Okay, so first of all, in order to apply that operator, I need to load some data. So what I'm going to do, I'm going to use the default data sets which are already there. So in the default data sets, as I told before, it is present in left-hand side. Under the repository panel, we have samples folder within which we have data subfolder. And within the default data sources I have, I'm going to use or load the Titanic data set. So in order to work on this data set, what you have to do, you have to drag and drop it into the process. And if you want to observe the data, you have to establish the connections first. After establishing the connection, you have to execute the process. Once that is done, you will get the results. In the results view, you can see the name of the view at the top. And here at the bottom, if you see, there are totally 1,309 records and 12 columns. And if you observe, there are question marks present in between. The question marks indicates that you are having missing values in your data. So we talked about missing values before when we are talking about data pre-processing. So what is the operator that I have to use in order to deal with that missing values? So I have multiple operators like replace, impute. I'm going to use the operator that is replace missing values. So here comes the operator, the next one that is replace missing values. Just take that into the process. The Titanic dataset got loaded in which I have a lot of missing values. And within the missing values, I'm just going to replace them. So I'm using the operator replace missing values. After using that operator, I'm going to use another operator. So if you want to select anything, you can select it. But I'm just remaining it as is. I want to replace all the missing values with the average value, which is median imputation. So I'm going to do that. And after that, what I want to do, I have to establish or I have to set one column as output variable. As this is a supervised machine learning algorithm, we already discussed about it. You should have input variables as well as an output variable. So what is an output variable? In the Titanic data set, if you observe, out of all the columns, which one you will replace it with a label, which is a target variable or an output variable? What is the last one? If you observe, the last column survived based on the input columns present or input variables present. We are deciding whether he is surviving or not. This is my output variable. Now, if you observe, this is not in green color. This is not a special attribute. So I want to make this as an output variable in this particular decision tree algorithm. How? For that, I will use the operator that is set role operator. So you have to take that again into the process. So set role into the process again, and the connections are mandatory. One operator needs to be connected with another operator. And in the set role, if I want to customize this particular operator, I should go for obviously the component called as parameters. Now, how will I deal with that parameters of set role? How can I set that survived column as output variable in this particular data set? So go to the parameters of this particular operator. You have here edit list. Click on edit list. And here you have to select which column you want to set it as a target variable. So I want to set the column that is survived column. So select the column name that is survived. And after that, I want to set it as a label, which means target variable. So you have to do that in this parameters of the set role operator, and you have to click on apply. Once you do that, execute the process and check out whether it is highlighting in green color or not. So see, survived is my output variable. Now that is survived. Out of 12 columns, 11 are regular attributes and 1 is the special attribute that is target variable. And after that, what? Okay, I've got the target variable. Now, after getting the historical data and setting the data up, which is replacing the missing values and then declaring which is your output variable, you have to split your data. So for that, I have an operator, split data. Yesterday, I've shown you one more operator that is cross-validation. I'll show you one more time. So split data, I'll just take it into the process now. As this is a machine learning algorithm, which is supervised, we already discussed 70% data goes into training and 30% basically goes into testing. So how to split your data? So go to the parameters of your split data and click on this option, which is edit enumeration. How many partitions you want? So I will add one entry as 70%, which is 0.7. And remaining 30% is one more entry, that is 0.3. There are two partitions here, 70% in one and 30% in another. And click on OK. After splitting your data, you have to apply the machine learning algorithm. What is the algorithm that we are discussing about? That is decision tree. So go to the operator here, the decision tree, and take it into the process. So 70% of your data goes into machine learning algorithm. So see here, I'll take it here. 70% goes into decision tree. After that, what happens? The rest of the 30% should goes into model, which is the operator apply model. And the decision tree output should first get into apply model. And after that, the remaining 30% of the data that you have splitted should get into apply model. After that, what? After that, you have to measure the performance. How can you measure the performance? By using the operator performance classification. Because this is not a regression algorithm, this is a classification one. So use the operator classification. Okay. Now again, connect everything. Apply model, the first one, gets into performance. And then this performance operator performance should be connected to the response port. And the apply model, if you want to see this, you can just take it to the response port. Depending upon your requirement, you can choose whatever you want to be connected as output. So what did I do? Here, I've just taken the data set Titanic, which is the inbuilt data set, which is already there in RapidMiner Studio. And after that, I've got missing values in my data. Now I'm replacing those missing values using the operator replace missing values. As we talked about before, if you have missing values in your data, you have multiple imputation methods present, in which I'm choosing average, which is median imputation. So now everything got replaced with the median wherever you are having null values or question mark. After that, as this is a supervised machine learning algorithm, I should set one column or attribute as an output variable or a target variable. So that I'm going to use the operator set rule for that. So set rule, in which I have just edited it or customized my operator based on the parameters. In the parameters, what did I choose? I've chosen the column name which is survived, and it needs to be label or the target variable. Anything is fine. And click on apply. After setting everything up, you have to split your data, which is the main thing in supervised machine learning algorithms. So for that, I'm going to use the operator split data. After splitting, 70% should goes into decision tree algorithm, which is what we are discussing about. And the rest of the 30% should goes into the model. And after, in order to measure the accuracy, based on what you are getting the accuracy, based on the comparison which was done between actual values and predicted values, you are getting the accuracy. In order to understand what is the accuracy level, in this, you are going to use the operator performance classification and just connect everything to the response port, the output port. After establishing the connections properly between the operators, you have to execute the process. So execute the process. So the first one you have is decision tree. This is how your decision tree is going to look like. The first node is passenger class, and remaining everything is internal nodes. And until when you have to just continue this process until you get the leaf nodes. What do you mean by the leaf nodes? Which means you may get only a single column as output, or yes or no, or both of the values having multiple records should be same. That is what you have to stop. That is where you have to stop the process of decision tree. And what is the performance level? If you check it out, the accuracy is 83%. But yesterday, if we applied KNN algorithm for different data set, I got 96. So for a single data, you can apply multiple outputs or multiple algorithms and check the accuracy and then decide which algorithm you can go for. This is the other supervised machine learning algorithm present, that is decision tree. And how to apply KNN algorithm here? How to apply KNN algorithm here? So let's just see one more time how to just do KNN algorithm. If you want to save this process, you can save it, but I don't want to save it. I'm just selecting all the operators and I'm just deleting using delete key, like delete button in the keyboard. Now I'm going to show you the KNN operator because we have discussed only one time yesterday. So for this, I'm going to use the iris data set which is present in my local machine. I'm not using this iris data set because it is already set it as a target variable for a specific column. So I want to use the data set which is present in my local machine, that is Fisher's iris data. That is a CSV file. So I don't want to store it in my repository. I just want to use it for temporary purpose. So I'm going to use the operator that is read CSV. Why only read CSV? Because the file that I want to use it here or import it here is a CSV file. And I don't want to save it in my repository panel. So I'm going to use the operator. So take it into the process. So how to connect with the data? You have to double click on the operator and you have to select which data set you want to use. I want to use the operator or the data which is Fisher's iris data, which is a CSV file. And click on next. Now, if you observe there is no change that is needed here, no problem is present at the bottom, you can check it out. If you want to change anything, you can change and click on next. And here the formatting is also fine and I will simply click on finish. Now I got my data. In order to understand about the data, what you have to do, you have to connect this operator to the output or response port and execute the process. Now, if you observe, there are totally 150 records and 5 columns present in my data. Now what? Now, as we are talking about KNN algorithm, that is K nearest neighbors, that is also another supervised machine learning algorithm. So what is mandatory in a supervised machine learning algorithm? That is an output variable needs to be there in your data. So for that, what is the operator? That is set role is the operator. So take the operator into the process. And always you have to remember the connections are mandatory between the operators in order to run the process. Now, which column or attribute needs to be your target variable? So I want my species column to be my target variable. So what is the target role? That needs to be label. Now, if I execute this or if I just click on apply and execute the process, I will get the column species in green color, which indicates that that is an output variable. Execute the process now. Now, if you can see here, now species is an output variable. Now what? Okay, I have just set my target variable. I've just got the data, which is properly present. I don't have any missing values present in my data. Now what? Now, I have to split my data. In order to split the data into whatever the partitions that you want, you have two operators here. One is split data that I've shown before in the decision tree. And second one is cross validation. And the second operator that you have, an alternative to split the data, that is cross validation. Just take that operator into the process, cross validation. After that, in order to get split, in order to understand which is the training and which is the testing data, you have to double click on this operator. Once you double click on cross validation, you can check it out. There is training here and testing partition, which is shown separately. In training, what happens? In training, you have to apply the machine learning algorithm. We are discussing about which machine learning algorithm, that is KNN algorithm. So take that operator into the process of training. So in the training phase, I got this one. The training data gets into the KNN machine learning algorithm. After that, I have to apply this model as well as the 30 remaining % of the data in the testing phase as well. So I have to use for this the operator called as apply model operator. Take this operator into the testing phase. Now again, you have to establish the connections from here to here, and testing data also goes into here. After just making the connections, I want to just measure the accuracy or performance. How? You have to use again the same operator, that is performance classification, because this is also not a regression based model. So I will take it here and again I will establish the connections here. And performance goes to performance, example goes to testing. So you have to check out which you are connecting properly. After establishing here the connections, you have to establish connections within the process. How to go back to the process? Here you can see the blue color process coming at the top. Just click on this process. After that, everything needs to be connected to the response. Testing, as well as I want to get the accuracy, so the performance as well. model, example, which means the records, and testing and performance. Everything needs to be connected to the response port. Now, check it out whether everything is present properly. See here, if you want to go again to the training and testing partitions, you have to click again on cross-validation. And again, process. Now, fine, execute the process. Now, check out what is the accuracy level. That is 96%. So, this is very good. The model which we are using, the algorithm that we are using, which is KNN algorithm, is working best for the data, that is iris data set. So that is the way you can do the predictions using machine learning algorithms, in which we are talking about supervised. Fine, KNN is fine. This is also fine. And how to work on the next one that we have discussed, that is naive Bayes. Naive Bayes algorithm, how to work on naive Bayes. I've already talked about naive Bayes before. Naive Bayes, the operator that we are going to use here is again naive Bayes. So how to work on the naive Bayes? That is very easy to work with. So here, I will use again the iris data set, but right now, maybe I will use the one which is already present, or this is fine. So iris data set, and again here I will have to set the rule, this is fine. And then what? I have to use the algorithm naive Bayes instead of KNN. So everything is same. I'll go back to this training phase. Instead of KNN, I will delete this one and I will apply the naive Bayes operator here and establish the connections training data here, and the result should goes into the apply model and execute the process. Now check out the accuracy. Now this naive Bayes is giving you the accuracy 94%. But for the same data set, for the same output variable based on same input variables, I got more accuracy using KNN. So by applying different types of machine learning algorithms, you can choose the best one based on the accuracy level. Okay, this is how we are going to work on in RapidMiner Studio. Now let's go back to the slides and check it out what is there after the decision trees. So we are done with the introduction for RapidMiner and how to perform EDA as well as data pre-processing, and what are the graphical representations, how to visualize your data in RapidMiner Studio. And then we have started discussing about the the model building or machine learning algorithms, in which we have supervised and unsupervised. In unsupervised, we have started discussing about three things. That is agglomerative clustering, which is also called hierarchical clustering. And in non-hierarchical, we have discussed about k-means algorithm or k-means clustering. And in order to overcome the drawbacks of k-means and also the agglomerative clustering, we have the next one, that is DB-scan. So DB-scan, what is DB-scan? DB-scan is based on density. And we have also seen the last one, that is association rules. In association rules, as I talked about before, it is useful to understand the relationship between items in a data set. So here you will have different types of performance measures like support, confidence, etc. We have seen yesterday. Those are what we have seen in unsupervised machine learning algorithms. As well as I've also shown you how to use or how to perform these particular algorithms in RapidMiner Studio as well. And coming to the supervised, we are done with naive Bayes. We have also discussed KNN as well as decision tree. The next one that we have is regression. The next module that we are about to discuss is simple linear regression. So we will check it out what is that. Let me open the slides for you. So the next one is regression analysis. So what is this one? What is this one? As we talked about, we are currently discussing about machine learning. Machine learning, I can also call it as data mining, or I can also call it as model building. Anything is fine. So within this, we are discussing about supervised machine learning algorithms. Supervised learning is also called as, what is the other name for supervised? Supervised machine learning is also called as predictive modeling, because we are doing the predictions here. We are building a model. Why? To predict some value based on the new data. So prediction, it is called as predictive modeling. So this is called as predictive modeling here. And what is it? In which we are about to discuss about the next concept, that is regression. So we have a lot of prediction models or predictive models present. Up to now, what we have discussed, the predictive models, we have discussed about KNN. We have seen how naive Bayes is working based on Bayes theorem, and how decision tree is building. We are building the decision tree, how it is working. We have seen all these things. There is another branch present for this predictive modeling that is called as regression analysis. There is another branch present for this particular predictive modeling. What is that one? That is regression analysis. So this is very old and very powerful. So when it comes to interpretation, for interpreting the results, we will choose the decision tree as the number one. So we will choose mostly decision tree when I want to interpret some results. And the next best one that we are about to choose is regression. And in which you again have two types. What are those? In which we will talk about again linear regression and also logistic regression. These are the other techniques present which are most widely used. So if your output variable is numeric, when should I go for linear regression and when should I go for logistic regression? As we talked about before, particular algorithms only prefer your data or output variable to be in numeric only. And certain machine learning algorithms will prefer your data to be in categorical only. Now, linear regression prefers what? And logistic regression prefers what? If your output variable is numeric, then we proceed with linear regression. If your output variable is numeric, we will proceed with linear regression. Now, if your output variable is categorical binary, then what? Then we will proceed with logistic regression. So what is it, everybody? We are discussing about the predictive models within which we have another branch which we did not discuss before, that is regression. So in order to interpret the results, the best one that we will choose, the first one is decision tree. And the next best one that we have, the most old one and the powerful one, that is regression. And in regression, again, you have two types. One is linear regression and second one is logistic regression. If your output variable is numeric, then you prefer to use or you proceed with linear regression. If your output variable is categorical and binary, you will use or you will proceed with logistic regression. Now, what is present in the slides? So this is prediction of numeric dependent variable. Now, let's see what is present in the slides. The first we will talk about agenda, what we are going to discuss about in this particular module. So we will discuss about the equation y is equals to f of x, which you already know about this. And what is the scatter diagram? And what is correlation analysis? We already talked about correlation when we are talking about scatter plot, which is a bivariate plot, which we have discussed when we are talking about graphical representations. And what is the equation of a straight line? And what do you mean by ordinary least squares? And finally, regression analysis. We will discuss the most important thing and how dummy variables are created. And what do you mean by simple linear regression with the help of a use case? And we have also seen the transformation methods. What are the transformations and how we are using those? And what do you mean by bias versus variance? These are the things that we are about to discuss in this particular module. Now, let's say the first one. The first one, the heading here is Bayes equation. Now, what is Bayes equation? This here is the Bayes equation. What is it? What we can understand from this particular Bayes equation. So here, it's not the output. It's the inputs that matter. We will consider the inputs. Any output that you want to achieve will depend on input variable. Maybe you may have a single input variable or you may have multiple input variables. Anything is fine. But we will mostly concentrate on input variables because based on this, we will get the dependent or the desired output. Now, single inputs like number of projects you complete based on that. You may have a single input variable like I have age column. That is numeric. That is a single input variable. So it may be one or you may have multiple inputs as well. So based on that, the inputs we are about to discuss about the output. So your output here might depend on a single input variable or it might depend on multiple input variables. Now, given this context, you have to focus on the inputs in order to set your desired outputs. That is what the Bayes equation is. If the output variable is continuous. So in this Bayes equation, you already know about y is equals to f of x, Y is nothing but output variable, and X is nothing but input variable, and F is a mathematical function. So here, we will mostly concentrate on inputs. Why? Because based on the inputs itself, we will get our desired output. And those input variables it may be a single input variable or it may be multiple. Okay, now if your output variable is continuous, then we don't consider whether the inputs are continuous or not. We will proceed with linear regression. If your output variable is numeric or continuous, we will not concentrate whether my inputs are continuous or not. I will just proceed with the linear regression. Another thing that you need to understand is that if you have a single input, then you predict your output. Now, this is called as simple linear regression. So, in linear regression, again, you have two types. So, what do you mean by single or simple linear regression and multiple linear regression? So, if you are having a single input, based on this input, I'm predicting my output. Now, this method or process is called as simple linear regression. Now, what about multiple linear regression? If I have multiple inputs, and again, I have output which is continuous, because linear regression works only when my output variable is continuous. Now, if my output variable is continuous and I have multiple inputs, then I will proceed with multiple linear regression. What is it? In linear regression, when do we use linear regression? When my output variable is continuous. And as we talked about, even though the output variable is continuous, the inputs may be single or multiple. So based on what you are predicting your output, based on a single input or multiple inputs, based on that, you have again two types of linear regression. So when I am predicting my output based on a single input, it is called as simple linear regression. And when I am predicting my output based on multiple inputs, then that comes under multiple linear regression. So let's see what is present in the slides. So the next one, we have a scatter diagram. So what did we discuss up to now? So we have started discussing about the next supervised machine learning algorithm, that is regression analysis. Within regression, again, you have multiple types. And for interpreting the results, we will choose this one for best. And here you have linear regression. Here you have linear regression and logistic regression. So in linear regression, again, you have two types, simple linear and multiple linear. So when do you go for simple, when do you go for multiple? So when you have output variable continuous, in both the cases, the output needs to be continuous, because that is when I'll go for linear regression. So the output variable is continuous. I'm predicting this output based on a single input. I have only a single input x1. Then I will go for simple linear regression. If I have a continuous output and I have multiple inputs, then I will proceed with multiple linear regression. This is what we have discussed up to now. The next one that we have is scatter diagram. We have already learned about the scatter diagram. What is the scatter diagram? This scatter plot talks about relationship between two continuous variables. What is the main function of this dual or bivariate chart? Why am I calling it as bivariate? Because it will use two columns in order to create this chart. So scatter plot, this talks about, or this understands the relationship between two numeric, or we can call it as two continuous variables. Now, what is the main primary purpose of creating a scatter plot? What are the primary purposes? What are the primary purpose? What is the primary purpose that we will go for creating a scatter plot? We have already seen these things. The primary purposes for this includes three things. One is it talks about direction, whether the direction between two continuous variables is positive or it is negative. Then it also talks about strength, and strength can be either strong or moderate or weak. And the third one it will talk about is relationship, whether is linear or non-linear, the linearity. So this is the primary purpose of creating a scatter plot or scatter diagram. So direction between the two continuous variables, whether it is positive or negative. What do you mean by positive? If one value is increasing, the other is also increasing. This is nothing but positive direction. If I have reverse, if one value is increasing, the other value is decreasing, then we will go for the direction that is negative. And what about strength? What about strength? So strength usually talks about whether the data points are closely packed or not. That is subjective. So coming to the secondary purposes, what are the secondary purposes that we have in order to plot the scatter diagram? What is the secondary purpose? When it comes to secondary purpose, we again have two here. One is we can identify the outliers in my data using scatter plot. And the second one is I can also understand the presence of clusters. Secondary purpose of plotting a scatter plot. One additional thing that you need to remember is that, as I told before, strength is usually subjective. So I will say the data points are closely packed, but the other person says these are not closely packed. They are clustered somewhat. That is subjective. The strength is subjective. Since it is subjective, that is the drawback. So now we have to evaluate the strength in objective. And how to evaluate in objective manner? You are going to use or going to give something called as correlation coefficient value. We are going to use something called as correlation coefficient value. This correlation coefficient value ranges between -1 to +1. And this correlation coefficient is represented using small r or r square, anything is fine. And if r value is greater than 0.85, then I can call the strength between the two variables is strong. If the r value is less than 0.4, then the strength between the two continuous variables is weak. If it is in between 0.85 to 0.4, then the strength is moderate. This is what we can just make the subjective drawback that we have based on strength into objective based on the concept called as correlation coefficient. This is what present in the scatter plot. A scatter plot is a bivariate chart. It talks about the relationship between two continuous variables, and the primary purposes that includes to create a scatter plot are we talk about or we understand the direction, whether the direction is positive or negative, and we also understand the strength, whether the data points between two continuous variables are closely packed together or it is clustered. So the strength is either strong or moderate or weak. And it also says whether the relationship between those is linear or non-linear. And coming to the next one, the secondary purposes, you have two secondary purposes here. One is we can identify the presence of clusters and we can also identify the outliers. And coming to the subjective part, the strength here is subjective. In order to understand in objective manner, we have something called as correlation coefficient value. That correlation coefficient is ranging between -1 to +1. And then it is represented using the r, small r, and the values. If the value of r is greater than 0.85, then I can call the strength as strong. If it is less than 0.4, the strength is weak. If it is in between, the strength is moderate. This is what is the purpose of a scatter plot. Let's see what is present in the slide. So here, scatter plots or scatter diagrams, it provides a graphical representation of the relationship of two continuous variables. And you have to be careful. Correlation does not guarantee causation. So correlation by itself does not imply a cause and effect relationship. And this is how your strong positive correlation is looking like. Why this is called strong positive? As one value is increasing, the other is also increasing, which means the direction is positive. And these are closely packed together. These are not clustered. So I can call it as strong positive. Now, what about the next one? The next one that we have is negative positive. What do you mean by negative positive? So this should be like this. This is okay. This is fine. This is moderate positive. So moderate positive, positive means what? The direction is like this. One value is increasing, the other is increasing. And coming to the moderate, here, if we observe the closely packedness of this particular chart compared with this one, these are not very close. So I can call the strength as moderate. If you want to get the accurate result in objective manner, instead of looking at the chart, you can go for correlation coefficient. And then next one, what you have? The moderate negative correlation. Negative means as one value increases, the other value decreases. So see, this is increasing, this is decreasing. And moderate is nothing but these are not closely packed. That is moderate negative. And the next one that we have is strong negative. Negative means this direction, and strong is these are densely packed, closely packed. That is strong negative. And what is the next one? Next one is no correlation. The data points are clustered. You don't have any correlation between those. This is how your chart will look like. If it is present in the form of a chart about linearity, that is curvy linear relationship. And in here, you may heard about polynomial with n degrees. How can we say polynomial with n degrees? What do you mean by n? So here you have a single curve. So that is one curve or one bend. One bend is nothing but this is n, and degrees will be n plus 1. So here, how can I call this as? This is a chart which is polynomial with 2 degrees, which means I have a single bend. If I have two curves like this, there is one curve here and one curve here. So n bends are there. And how many degrees then? N plus 1, that is 2 plus 1, 3. So this is polynomial with 3 degrees. And bends is nothing but what? Number of peaks and number of troughs. You already know about this. This is the simple thing about scatter diagram and correlation. And what else? So here see, judge the strength of the relationship by width or tightness of scatter. Determine the direction. If x increases and y decreases, it is negative. If x increases, y increases, it is positive correlation. That is nothing but we have discussed the things. The next one we have is correlation analysis. So what is correlation analysis? Correlation analysis measures the degree of linear relationship between two variables. What is this? So the R value based on the width of data points, if the closeness of or if the data points are close together, then the R value will be more. If the data points are closer together, our correlation value or correlation coefficient value will be more. And if the data points are not closer, then the R value will be less. And we will check out what is present in the slide. So here, this correlation analysis measures the degree of linear relationship between two variables. The range of correlation is -1 to +1, and perfect positive relationship is +1, perfect negative is -1, no linear relationship is 0, and if the absolute value of the correlation coefficient is greater than 0.85, that is a good relationship. So see here, now you have R value 0.87, 0.9, minus 0.9 and 0.87. Now describe the good relationship here. Describe the poor relationship here. Now what does that good relationship means? Which is greater than 0.85. Compared with all the values, this is greater and this is greater. Out of which is more, 0.87 or 0.9. So 0.9 is more. So this is the one which is having good relationship. And coming to the poor relationship, if it is less than 0.4, that is very weak correlation or closer the data points are. So 0.4, you have minus 0.5. This is the one that is having very poor relationship. That is how we talk about the relationship between two continuous variables using correlation. Correlation values of -1 or 1 imply an exact linear relationship. However, the real value of correlation is in quantifying less than perfect relationships. We can perform regression analysis, which attempts to further describe the type of relationship if the correlation is good between the two variables. This is about correlation analysis. Now, what is that? See here, these are the data points. Now, if you observe here, is this positive or negative? It is positive. Why? Why it is positive? Because the data points are scattered, but still it is having some direction. So if you observe here, if this value is there, I'm just comparing one variable with another one. So for this data point, the x value is less and y value is fine. For this x value is more, for this x value is more, for this x and y are more, for this x and y are more, for this x and y are more. So every time when I go up, the value of x increases as well as y increases. So the direction is positive. And coming to the correlation, the R value is 0.4. If it is in between, I can call it as moderate. If it is in between 0.85 to 0.4, okay, I can call it as weak because this is 0.4. If it is less than 0.4, I can call it as weak. This is equal, so I can call it either moderate or weak. Okay, now this is positive correlation. And what is the next one present? Okay, sorry. The next one that we have is here, see, this is not having any correlation because this is clustered. Whenever our R value is -1 and +1, exactly, I will have a linear relationship. This is negative direction and this is moderate. R value will be again 0.4 or something. So see, less than 0.4, then this is weak. And here is your formula for finding out the correlation coefficient. Okay, the next one. What is the next one present? The next one that we have is equation of a straight line. So what is equation of a straight line? You already know about this. The equation that represents how an independent variable is related to a dependent variable. And an error term is a regression model. We will talk about this later. But equation of a straight line, you know about it. What is that? Y is equals to c plus mx or mx plus c. So here y is the output variable and m is the slope, x is the input variable, and c here is the y-intercept. Instead of this, we have multiple things present here. So here, these are nothing but the coefficients, the beta values, and this we will talk about these things later. What is it? So here, beta naught and beta 1 are called parameters or coefficient. This is the random variable called error term. We will talk about this later. So this is the formula or equation of a straight line that is written in this format for regression. And what else? So here is your formula for beta naught and beta 1. You can go through these formulas later. And coming to the next important thing, that is ordinary least squares. What is ordinary least squares? So, suppose you have here a chart. So what is this chart talking about? Observe here. So here is my chart in which on x-axis I have something, on y-axis I have something. So on x-axis maybe I have the waist circumference, the waist measurements, 36, 38, something like that. The waist measurements are present here. On y-axis, I will take the adipose tissue. Adipose tissue. Okay. Now, for every patient, you have the waist circumference as well as the adipose tissue. And if I plot it, I got this chart. Now, every data point here is the waist as well as the adipose tissue. So now this is my actual data. What is it? This is my actual data. If this actual data falls along a straight line, I can call this as it is having a linear relationship. If these data points are falling on a straight line, I can tell that it is having a linear relationship. Now, if I want to capture the patterns in the data, then what I can do? If I want to capture the patterns, then I will get the equation of a straight line. What is the equation of a straight line? That is y is equals to mx plus c. So we have already seen the formula, how we can write for regression. What is it? Y is equals to beta naught plus beta 1 into x plus, if you want to write, you can write it as error as well. Anything is fine. Now, suppose that there is one line. There is one line here and I will call it as A. I'll call it as A and I have one more line. I will draw it here. I will call it as B. I have one more line. I'll call it as C. Now, which of these three lines do you think we can capture the patterns well? I have three lines. I've randomly drawn it, okay? So, I have three lines. I named it as A, B, and C. Out of these, which one is best for us to capture the patterns well? Is it A, is it B, or is it C? The patterns in the data is captured well in A. Why? Why? Because the data points are closer to this line. But when I compare the data points to B and C lines, these are far away. When we compare the three lines present A, B, and C, the data points are very much near to the particular line called as A. So this is more suitable for me in order to capture the patterns in the data. Okay, so if you see here, if I have infinite lines, suppose if I have infinite lines like this, if I have infinite lines, how could I decide which line is more chosen? It will be challenging for me. For that, people have come up with an algorithm called as ordinary least squares. So if I have infinite lines, which one or which line I should choose to capture the patterns well, that is not understandable for me. That is very challenging for me. So for that, I have an algorithm called as ordinary least squares, which is also called as OLS. In this, what you do, you find the distance between each data point to the line. See here what is happening. In this, we will find the distance between each data point to the line. Each data point to each line. See here. So what do we do? The distance from each point to the line, each point to the line, each point to the line. We will find all these things. We will find the distance. All the data points are your actual values. These are all the actual values. And these lines that you're getting are the prediction values or prediction lines, based on which I'm going to predict the future. Based on the prediction lines, I'm going to predict the future. So now you try to find the difference between the actual data points value and the predicted value. When I do this, what I will get? What is it? I got the actual values, which are the original values. When I just find the distance between the actual and the line, I got the predicted lines. This line is called the predicted line. Based on this, I'm going to predict the future. The right way to call this predicted line is fitted line. This predicted line, we can call it as fitted line. Now, what is this fitted line? Fitted value is called as a predicted value, which we will talk about later. Okay, so there are predicted values that I'm getting. Those are called as fitted values. Fitted values are called as predicted values. Why is it? We will talk about it clearly later. Now, when I subtract actual values with the predicted values, now I will get here an error. A minus P, I will get an error. This error is also called as residual values. This error that I'm getting when I'm subtracting the actual data points or values from the predicted ones, those are called as residual values. And when do you call this as error and when do you call this as residual value, you have to understand. Now, for all the data points, if you have found the predicted values and then you found the difference between actual and predicted value, you will get the errors. Now, you have to take all those errors and you have to square them. You will get errors when you do the subtraction between the actual values and predicted. And for the errors, I will square those errors, what I got for all the data points. Now, when I square them, you already know the positives and negatives will be cancelled out. Since they got cancelled out, they spread all the errors. You will get the sum of squared errors. You will get sum of squared errors. In all these lines that you're going to draw, you need to find out which line is having the minimum or the least sum of squares. That becomes your best line, and that is called as ordinary least squares. What is it? You have plotted a chart and you want to understand which line I have to choose in order to predict my values. That is called a predicted line or a fitted line. So which one you will choose? When you have limited number of lines, you can choose the line whichever is closer with all the remaining data points. But when I have infinite lines, I can't choose it manually. So that I have an algorithm called as ordinary least squares, which is also called as OLS. In here, what we are doing, we are finding the distance between each data point to the predicted line or the fitted line. And now, when I subtract the actual values and the predicted values, I will get some error. That error is also called as residual value. Now, whatever the errors that you're getting for all the data points, I have to square them. And once I do the square, all the negatives and positives will be cancelled out. Now, out of all the ones, the line I have to choose should have the least sum of squares. That is your ordinary least squares algorithm. Okay, so here, if you observe here, so this part over here is called beta naught, and this one is called beta 1. This portion is called here as beta naught. This portion, which one? this portion. Now, this is called as beta naught. And how? And you have to understand how steep your line would determine your slope. You already know about slope. How steep your line will talk about your slope. Whether your slope is beta 1 or beta naught, whatever it is, beta 2, beta 3, this will be talked about with the help of beta 1. Now you have beta naught intersect and beta 1, that is slope. And this intercept, these are called as intercept values, or we can also call as y-intercept, or we can also call as constant. Now, m into beta 1 are nothing but slope values. M beta 1. Here m in our equation, general equation, here beta 1. This is my slope values. If you don't want to build any prediction models, we have talked about this before. If I don't want to build any prediction models by just applying the machine learning algorithms or whatever it is, I should use something called as baseline model. I should use something called as baseline model. Now, what is baseline model? In your data set, imagine you have waist, which is an input variable here, and you have adipose tissue, which is an output variable. Now, if you take the average of output, I will get one value, that is nothing but y average. And if I take the average of input, I will get x bar, that is x average. If you don't want to build a model, then you don't have any beta naught or beta 1 values. So now the result is average. So whatever the value of input may be, your output will remain the same, that is beta naught. If you take the average of your output variable, that will be your baseline predicted value. So here you have an average value of y bar. This is your output for baseline model. But that is not the same thing when you build a model. If you don't want to build any model, you can go for baseline model, in which your predicted value will be the average of the output variable. Okay, suppose you have a data set where you have your output variable and input variable. The output variable is adipose tissue. The output variable is adipose tissue, and the input variable is again waist circumference. Now what I have to do? I have to do the average and I have to subtract the actual and predicted. That is your average, that is called as deviation. It's nothing but it is like variance. For each observation, for suppose you have 200 records. Now you will have 200 deviations because 200 predicted values you have, 200 deviations you have. If you have y and y bar, which is nothing but deviation, and when you square it, you will get the sum of squared errors, SST. You can call it as sum of squared values, anything is fine, SST. Now, if you want to build a model, then you will obviously get an equation, that is y cap is equals to beta naught cap plus beta 1 cap into x. Now, when you take each of your input variable and substitute here in the equation, you will get the predicted values. Now, you have x, which is waist input. You have y, that is output, adipose tissue. And then you have the baseline predicted model, that is y bar, average value. And your predicted model for this particular algorithm, that will be y cap. This is your predicted value for this particular model building. And y average will be your predicted value when you don't want to build a model, when you want to go for baseline model. When you subtract baseline model and predicted values, this is called as sum of squares regression. If I do y cap minus y bar, which is predicted values of one model and predicted values of baseline model, if I square them, I will get here sum of squared regressions. I will get sum of squared regressions because you have built a regression model here. Now, how this is different from a baseline model, you have to understand. One more thing you have to remember, that is SST that we have described before is equals to SSR plus SSE. What do you mean by this? So this measures the quality of X as predicted by your predicted values. And this talks about, or this measures the errors in the prediction. E stands for errors. This talks about errors in the prediction. This talks about the quality of X as predicted by your predicted values. Okay. Now, if I want to talk about beta or R square, how can I talk about R square? If you see here, what is the formula? SST is equals to SSR plus SSE. Now, basically, I will write R squared formula as SSR by SST. How can I write this one? And here I can write it as 1 minus SSE by SST. Okay, now how can I write it? See here. Here, if I take this to the left hand side and this to the denominator, whatever it is. So here what I can write, SST minus SSE divided by SST. I can write like this, is equals to SST by SST minus SSE by SST. Now these two will get cancelled. Now what is this? 1 minus SSE by SST. This is nothing but the R squared value, which is the general formula. R squared value, what is the formula? 1 minus SSE by SST. This R squared value will talk about the goodness of the fit. This R squared value ranges between 0 to 1, and in a simple linear regression, it ranges between -1 to +1. And R squared value is called as coefficient of determinations. We will call it as coefficient of determinations. Let's check out what is present next in the slide. So you have to just understand these things. This is y-intercept. This is error term, which is the deviation happening. This is the observed actual value, and this is the average value. And the straight line defines the equation, which is the linear y is equals to beta naught plus beta 1 into x. And this a specific value of x, the dependent variable. Fitting a straight line by least squares, this is your equation. Now, coming to the regression analysis, we talked about R squared is also called as coefficient of determinations. It represents the percentage variation in output or dependent variable explained by various input variables, or percentage of response variable that is explained by its relationship with one or more predictor variables. And higher the R squared value, the better the model. Mathematically, SSR measures an explained variation. It measures unexplained variation, which is errors, and SST is equals to SSR plus SSE. R squared value is always in between 0 to 1. And if it is in between 0.4 to 0.85, that is moderate. If it is greater, that is strong. This we have already seen before. And R squared value is equals to SSR by SST. This is your formula. And R squared value ranges between 0 and 1. So we will talk about this after the break. We will take a quick 10-minute break and we'll get back here. Okay, everybody, let's continue with the session. So what we are talking about, we were talking about the regression analysis here. So what is that we have discussed? We have seen about the R squared value. So R squared value is nothing but 1 minus SSE by something. Okay, so what is there here? So prediction and confidence interval. These are the types of confidence intervals that we are using for prediction in regression and other linear models. So we will talk about this clearly. And what do you mean by prediction interval? And what do you mean by intervals? So when you use the equation y is equals to beta naught plus beta 1 cap of x, when you are analyzing your data, but suppose we are talking about the adipose tissue output variable here, you will get one predicted value. You will get one predicted value. Since that is a single value, the probability associated with a single continuous variable is always zero, which we have talked about before. But suppose you have a continuous variable like, I want to find out probability of a person whose age is 85 kgs. This is a continuous value. He may be 84 point something, he may be 85 point something. So there are multiple infinite possibilities present. So the probability of a single continuous variable is always zero. So when I am getting a single predicted value here, probability is zero for that. Hence, we need to come up with intervals instead of discrete data. So that intervals, it can be either prediction interval or it can be confidence interval. And prediction interval, it ranges or it is the range of value within which each observation falls. It is a range of value within which each observation falls. Now, what do you mean by confidence interval? Confidence interval is that interval within which the average value falls. Check it out. So confidence interval is representing a range that the mean, which means the average, is likely to fall within the predictions. If your output variable is continuous, the prediction interval is always wider than the confidence interval because of the added uncertainty. And you can check it out, the confidence interval and the confidence interval and then the prediction interval here. So prediction interval is nothing but the range of values within which each observation is present, and confidence interval is nothing but the interval within which the average value is present. This is nothing but the regression analysis, and later on you have an use case present. So check it out here. First of all, if you have an output variable that is continuous, you obviously go for the type of regression that is linear, not logistic. And in linear, again, you have simple and multiple. So what do you mean by simple? When do you go for simple? When you have a single continuous input variable, then you will go for simple linear regression. And when you go for multiple, you have multiple inputs. So see here, simple linear regression, you can go for the single continuous and single discrete input variable. And when you have discrete input variables, what do? You will do the dummy variable creation. What is dummy variable creation? That is zeros and ones. We talked about this before when we are talking about the concept encoding. So dummy variable creation, we will use this concept to convert the discrete input into continuous. And then we will apply simple linear regression. Okay, then what? Then what else? So here, what do you mean by dummy variable? See here, first suppose you are having a gender. As I told before, in one hot encoding method, if you have n levels present in a factor, what do you mean by a factor? Factor is nothing but that attribute which is having very limited values. So gender is a factor here because it is having either male or female, limited values. So within the factor, if you are having limited values, if you are having different levels, based on the levels, you will get the number of new columns. In one hot encoding, if I have two levels, I'll get 2 plus 1 columns or 2 columns. So here male and female are there. I will obviously get 2 columns, male and female. So n levels are there, n columns in one hot encoding. N levels are there, n minus 1 columns in dummy variable creation. So I have 2 levels here, male and female. So I will get only 1 column, that is dummy variable. Wherever your male is present, there is 1 and female is 0 and so on. This is how you will do the concept called as dummy variable creation. Okay, next what? What is the next thing? What we have to do next? Next, we will see one use case for this linear regression, simple linear regression. Check it out. So simple linear regression, the use case. So here, the waist circumference and the adipose tissue data is present. And studies have shown that individuals with excess adipose tissue in the abdominal region is having higher risk of cardiovascular diseases. So, computed tomography, commonly called as CT scan, is the only technique that allows for the precise and reliable measurement of the adipose tissue. The problems with using the CT scan are many physicians do not have access to this technology. And then irradiation of the patient suppress the immune system, and it is very expensive. So here, first of all, when you are working on a project, what we have to understand? We have to understand our business problem. What is our business problem? So what is our business problem? Here, if your adipose tissue is very more excess, then you will have a risk of cardiovascular diseases. That is your business problem, in which adipose tissue is the output variable and then waist circumference is the input data. Once you understood about the business problem, you have to go through the objective, your constraint, and then success criteria. So see here, these are the problems present. Is there a simpler and reasonably accurate way to predict this adipose tissue area? CT scan is very costly. Everybody can't go to that method in order to understand the precise of the adipose tissue. Now, easily available, it should be risk-free, it should be inexpensive. A group of researchers conducted a study with the aim of predicting the adipose tissue area using simple anthropometric measurements like measurements on the human data. The waist circumference and adipose tissue data is the part of the study, wherein the aim is to study how well the waist circumference predicts the adipose tissue area. This is what our problem. We have to predict the adipose tissue area based on the waist circumference. Now, see here. Say you have totally 109 patients. You have their waist, which is input variable, their adipose tissue value, which is output variable. But you did not measure the waist. You did not measure the waist circumference. And you did not do any adipose tissue measurements as well. Now, adipose tissue measurements, you got it from CT scan. And waist is usually by measuring tape. We are measuring our waist and you will get it. Okay, now, in the output variable, if this output variable, in this, you can observe the output variable is continuous. What is it? The output variable is continuous and the input variable is also continuous, but this does not matter for us. So now I can go for linear expression or linear regression because this is a continuous output variable. If I have single input, I will go for simple linear regression. You already know about this. I have only single input variable. I will go for simple linear regression. Now, how to work on this in practical manner, and let's see what is present in the slide, then we will discuss about it in RapidMiner, how to do it. So we will talk about this simple linear regression in RapidMiner Studio, how to do it, what is the operator used, and how can I get the results or accuracy for this particular supervised machine learning algorithm. Let's check it out. Let us open the slide. Let us open the application that we're currently working on. So this is what we are working on. I will delete everything here. So I've deleted the process that I've previously created. You can just save it and use it for the future purpose. But I don't want to save it, so I just deleted them. Now I want to work on this particular application regarding what? Regarding simple linear regression. Now, how to work on simple linear regression? How to do it in this particular application, RapidMiner Studio? How can I do it? So here I'm going to use the data sets which are inbuilt present in this particular application. So where can you see the inbuilt data sets? With, inside the repository panel, within the samples folder, within the data subfolder, you can see all these things present. Now, within which I'm going to choose the data set golf data. In order to use it, I have to bring it into the process. Okay, golf data, I have got it. Now what I do, I will just establish the connection to look at the data, to have an understanding about the data. Just run the process. Now see here, you have output variable which is already decided, that is play. Based on the outlook, based on the temperature, based on humidity, based on wind, I am going to predict this play. But this is simple linear regression, so I need to have only one input variable. You can choose whatever you want, either temperature or humidity or wind, anything is fine. Now see here, I'm going to use this first one, the operator, that is generate attributes. Why? Why? Because if you observe, first of all, you have to understand whether I can apply the linear regression here or not. How can you understand about that? So, as we talked about before, when do I choose linear regression? When my output variable is continuous. When my output variable is continuous. But here in this example, I have an output variable. What is the output variable? That is play. So play is not present continuous. It is categorical data and it is binary still. So I can't go for linear regression. Now, how can I go for linear regression if I want to? I have to convert this into numbers. How to do it? See here. How to do it? See here. I will go here. If you are about to work using the operator binomial to numerical, that is fine. But you can also go for the new one, which I haven't shown you before. That is generate attributes. I'm going to generate a new column. So I'm going to generate a new column. And how do I customize this operator? By using its parameters. Now, how can I go to the parameters of this operator? Click on this operator, go to the parameters on the right-hand side, and click on this edit list. When you click on this edit list, it will ask you for the name of your new column or attribute. What is the name of my new column? That is play, which I am encoding. So play encoded is my new column name. Now, what is the function? You can just check it out using this calculator as well. You can just use whatever that are basically present. I'm going to use the if function, which is a logical function. And within the logical, I'm going to use if. Now see, here is the syntax. If condition, your true value, false value. See here. My condition is, if the play value is yes, then I should get 1. So you have to select your attributes here. Check it out. Play. Play is equals to, within single quotes or double quotes, yes. You have to check whether S is present in uppercase letters or lowercase. You have to check that. Mine is in lowercase. So 1. And if it is false, I have to get it as 0. This is my condition. If the play is equals to yes, I want to get the output as 1. If it is not yes, I want to get the output as 0. Now click on apply at the bottom. Here is my condition. The play encoded column will have only zeros and ones. Why? Because I want to apply here the algorithm that is simple linear regression. If I want to apply simple linear regression, I should have the first case that the output variable needs to be continuous. So the output variable is not continuous now. I am making it continuous by encoding technique. Click on apply. Now I've got this one. Now execute the process and check out whether the play encoded is having zeros and ones or not. Check it out. So you can see the new column. Wherever S is there, it is replaced with 1 or it is having 1 here. If it is no, it is showing as 0. The play encoded column is fine. Now what else? Now, if you are not having any output variable, then you have to check your output variable. Now, what is my output variable? My output variable is not play. I want the play encoded as output variable. How to change this as a regular column? How to change this as an output variable column? For this, you have to use the operator before I have shown it to you, that is set role operator. So take it into the process. As I told before, you have to understand the theoretical part, which algorithm I'm going to use and what is the requirement that I need to satisfy to use that algorithm, whether it is supervised or unsupervised, and which operator I have to use it for which purpose. If you know these things, you can easily use this in RapidMiner Studio without writing any code, as I shown before. Now see, I'm going to set my play encoded column as the output variable and the play column as a normal column. Now how to do it? I have to use the operator set role. And after that, if I want to customize, I have to use the parameters again. How to use the parameters again? So you have to click on this operator and go to the parameters where you have edit list. Now what I want the play encoded column to be as the target variable. play encoded as label. But already I have one column which is in green color. What is that column? That is play column. I want to make it as a normal regular column. How? I will add one entry and I will take the column play and I will make it as regular. That is not a label now, that is a regular. Now apply it and execute the process and check it out. Now play encoded is the output and play is the normal column. Now what? Now this is the simple linear regression we are talking about. So simple linear regression works with only one input variable, not with multiple. So what I do, I will just use the operator called as select attributes. Because I want to select only one input and one output. I don't want remaining else. So I'm going to use the operator that is select attributes. I'm going to take it into the process. Now I want to include a subset. What are those? One is the output variable play encoded. And second one, you can take anything you want. Temperature, humidity, anything is fine. I will take temperature. Based on the temperature, I have to check whether a kid can play or not. Okay. Now click on apply. Now execute this particular process. You will get only two columns. Now, what I have to do, I have to just split the data into two parts so that I can apply my machine learning algorithm. How to split your data? You can go for cross-validation or you can go for split data. Anything is fine. I will show both of those. First, I will show you split data. So I'm taking the split data into the process again. Now, what do you want to split? I want to split here according to the parameters. First should be 70%, obviously. And again, I will add one more thing, which is 30%, 0.3. And click on OK. I got two parts. One is 70%, second one is 30%. After this, 70% of my data should get into the algorithm that is linear regression algorithm. So I have to take the operator linear regression here and 70% of my data. The first part goes into linear regression. And after that remaining 30%, it should be applied to the model. So I have to apply or use the operator apply model here. So see here, the output of linear regression is the first input of apply model. And the 30% data which is present in the split data is also going into apply model. Now I want to measure the performance. You should not use the operator performance classification here because this is not a classification. This is a regression model. So you have to use the operator performance regression. You have to use the operator performance regression and just establish the connections. This one is needed to be connected here and connect everything to the output port. You want performance and example, you can connect it. Or if you want to show the linear regression, you can connect it here. Anything is fine. Now execute the process. If you don't want to connect linear regression, that is also fine. You can check it out, both of those here. Execute the process and check it. So this is how your example set is present, the play value, the encoded, and the prediction values, the original and the encoded. Now you got the R-squared error value. What do you want to know? You have to get the least R-squared value, that is OLS. So you have to check out which one is having which least value, 0.458 plus or minus 0.000. This is nothing but the performance vector. If you want to see the description, you can check it out here. Okay, so this is what is present in simple linear regression. As I told, if you want to just split the data, you can either go for cross-validation operator as well. How can I go for cross-validation? See, I'm deleting these. Now, instead, what I do, I will just use the operator cross-validation. Both are same, but both are basically useful for splitting your data. Now, if you want to get this cross-validation properly, you have to double-click on it. And which algorithm we are talking about? Linear regression algorithm. Take your linear regression and get it here. Establish the connections here. And then take the next one that have to be in the testing one. That is apply model. Take it into the testing. establish the connections again. And the last one that we have is performance measure, that is performance regression, because this is a regression technique. Establish the connections here, performance to performance, example to testing. Connections are done. Check it out for the cross validation whether the connections are properly present. These are present, fine. Now execute the process. Now see, this is your linear regression and it will additionally give you coefficient and tolerance. This is what you can get when you are using cross validation. This is about simple linear regression. When do you go for simple linear regression? When you have output variable that is continuous, you'll go for simple linear regression, and that may be continuous or discrete. Anything is fine. If you are discrete, you will go for dummy variable creation. So if you have an input variable that is continuous, it is fine. But if it is discrete, then you have to go for dummy variable creation or encoding technique. This is how we will perform the simple linear regression in RapidMiner Studio. Okay. So up to now, what did we discuss? What did we discuss? We are talking about supervised machine learning algorithms, within which I have shown you the first one, that is naive Bayes. The naive Bayes is the operator, and I've shown you for iris data set. And I have done the same thing for iris data, which is k nearest neighbors as well. When compared these two, I got more accuracy in KNN. Now, the third one that I've shown you is decision tree. The operator that I will use here is decision tree. And the fourth one that we are talking about is regression, in which I have linear and logistic. In linear, we are talking about simple. For both of those, we will use the operator linear regression itself. This is what we are talking about in the current trees. Now let's see what is present in the mind map. So we are talking about the next one. So see here, regression models. Shallow machine learning models is done. Now let's talk about regression models. So in regression, we are talking about simple linear regression. So simple linear, the output variable needs to be continuous and input variable is single. And evaluate the p-value of each coefficient. P-value should be less than 5% to say that the coefficient value is statistically significant. Evaluate the overall p-value and evaluate R-square value. And then evaluate the model assumptions. We'll talk about these assumptions in the coming session. And you have to check for the moderation effect and the baseline model. We will talk about this now. See here. So the next one that we have is the multiple linear regression. What is multiple linear regression? What are the assumptions? I'll tell you in this session. In this particular module, we will cover it. So here, we are talking about whether the output variable is continuous or not. If it is having single input or not. So if you are having an output variable that is continuous, and then you use a single input to predict it, you will go for simple linear regression. If you have output variable that is continuous, but multiple inputs, then I will go for multiple linear regression. That is what it is present. Now let's see what is present in this particular module. So what is that we are going to discuss here? What are the regression techniques present and dummy variables? What are the model assumptions? Multiple linear regression. What is the use case? And what are the regression insights? These are the things that we are going to cover in this particular module. Now, what is regression techniques? What are regression techniques? So as we talked about before, if the output variable is continuous and the input variable is multiple and continuous, I will go for multiple linear regression. If you are having continuous output variable and the input variables are multiple and discrete, I'll go for multiple linear regression, but I have to do the dummy variable creation again. So this we have talked about in single as well as here also the same, that is multiple inputs. Now, what do you mean by dummy variables? This is how you will create dummy variables. If you have a column that is make of a car, either it is petrol variant or CNG variant, whatever it is, if you have this column, then you will create the dummy variables in this way. So see here, zeros and ones. When it comes to your regression analysis, as we talked about, see here, what is present next. when you are talking about regression analysis, we will have the equation like this. This is your equation of regression. Now, you will have here this particular symbol, which is called as epsilon. This is a Greek notation or a Greek alphabet. Now, suppose you predict the sales of next month. Suppose you are going to predict the sales of next month. So you have actual sales and you have predicted sales. Actual sales, I will take it as Y, and predicted sales, I will take it as Y cap. So I'm going to predict the next month sales. I'm going to predict. Suppose I got the predicted sales as maybe $1 lakh. Anything is fine. 1 lakh rupees. Anything is fine. Now you predict. You will have Y cap, that is the predicted value. When you will know about the actual values or actual sales value of that month, when you will know this actual sales value of that month, until I reach the last of the month or end of the month, I won't get the actual sales value for that month. So you won't know the actual sales till the end of the month. So what do we do in such case? Maybe once I reach the end of the month, I understood my actual sales. Maybe I got it as 80,000. I got the actual sales as 80,000 and the predicted sales is 1 lakh. Now, when I subtract both of those, I will get 20,000, which is nothing but my errors. As we talked about, when we subtract the actual values from the predicted values, you will get the error. Hence, while you are building your prediction model, only this part is known. What is that part? See here, this part. Only this part is known. The epsilon value we won't know when we are building the model. In simple linear regression, we have understood that we need to look at whether the relationship between the input variable and output variables are linear or not. Okay. Second point is, when it comes to multiple linear regression, we need to check whether the relationship between the output variable and the parameters, which are beta values, it is linear or not. We have to understand. I have to find out. What is it? In simple linear regression, we have to understand the relationship between output and input variable. But when it comes to multiple linear regression, we have to understand the relationship between the output as well as the parameters, the beta values present here. When you are building the model, you don't know the epsilon value, only these values you understand. Now, if you have the equation, what is the equation? Y is equals to beta naught plus beta 1 into x or something. So I will just write it as using log equation. If I say y is equals to beta naught plus beta 1, log into x1. Now, this is linear. Why this is linear? Why? Because this is in the form of the equation y is equals to c plus mx. This is the equation of a straight line. So I will tell this is also linear. If you have the equation like this, y is equals to beta naught plus beta 1 into x plus beta 2 into x square. This is also linear. Why? Because the relationship between beta and y are linear. This is also in the form of straight line. So now, we talked about before the fitted values. The fitted values are also called as residual values. What is it? The fitted values are also called as residual values or residuals. And the errors. No, what did we talk about before? Fitted values are called as residuals. Sorry, errors is called as residuals. What am I writing? Okay. Errors are also called as residuals and fitted values are also called as predicted values. So now we will just understand the relationship between fitted values versus residuals, errors as well as residuals, which is nothing but the fitted values. We have to understand the relationship between these or residuals or predicted values or observed values or predicted values or actual values or fitted values or predicted values. Everything is fine. We have to understand the relationship. Assume that errors and residuals are same and fitted values and predicted values are same. Next, there is something called as independent. Next, we have something called as independent. We have some assumptions about the errors. What are those assumptions about the errors that we have? What are those? Errors are independent of one another. See the assumptions, everybody? That is what present in your mind map. So, linear in parameters, residual versus fitted value, observed versus predicted. And then the next one is we have assumptions about the errors. What are those? That is independent and identically distributed. What is that? The errors are independent to each other. If you have all the observations and errors, and you don't want the errors of one observations to be low and the errors of one observation to be high, you don't want in that way. So you want them to be identically distributed. That is one assumptions present here. Okay. Now, when you want to build a model where the errors are independent of each other, that is the assumption about the errors. When you look at your errors or residual values and plot a distribution, probability distribution, they should be normally distributed. Either look at your histogram, you can plot a histogram, or you can plot a QQ plot or a box plot. Anything is fine in order to understand your shape of your distribution, whether it is normally distributed or not. So the errors should be equally distributed and they should be independent. And what is the next one? So there should be zero mean. So when you take the mean of the errors, it should be approximately equal to zero, the mean of the errors. And then it should have a constant variance. The variance should be constant. That is called as homoscedasticity. If there is no constant variance, it is called as heteroscedasticity. If you are not having no constant variance, that particular problem that is going to arise is called as heteroscedasticity. You have to remember these things, which we will talk about in logistic regression as well. Okay. Now, these errors are independent to be each other. If they are not independent, you will get the autocorrelation problem. What is it? The errors need to be independent of each other and they should be normally distributed. And when I take the mean of the errors, it should be approximately equal to zero. And the variance should always be constant. If it is not constant, you will get a problem called as heteroscedasticity. And if the variables or the errors are not independent to each other, then that is called as autocorrelation problem. And what else? What else are there? Now we also have assumptions related to predictors. What do you mean by predictors? For all these problems that we have here, you have one solution. What is that? That is nothing but transformation. For all these things that we have related to the errors, I have one solution. That is, I can go for transformation. The next one that we have is assumption about the predictors. Predictors are nothing but the input variables. Predictors are nothing but the input variables. The inputs that you are choosing for your model building, those are called as predictors. Now, these predictors need to be non-random. Non-random. So in multiple linear regression, you will have a single output variable and you have multiple input variables. So what input variables that you have to choose to build your model, you have to think about it carefully. So that should not be non-random. That should be non-random. That should not be random. Now, these are measured without any error. There will not be anything without correlation. What do you mean by correlation? You already know about correlation. Suppose if you are having a high correlation, then you will have the problem here called as collinearity problem. See here. So this is measured without any error and these are independent of each other. If not, we will have a problem called as collinearity problem. T-test concludes that the coefficients are not statistically different from zero and F-test is significant. And what about the assumptions about the observations? Assumptions about the errors, assumptions about predictors, assumptions about observations. These are called as line assumptions or modal assumptions. So see here, assumptions about the observations, they should be equally reliable. Suppose you say you have 1,000 observations. Suppose you say you have 1,000 observations. Every observation that you're capturing should be equally reliable. You can't say until 400. Do not do this, whoever is doing that. So here, you can't say 400 observations. Up to 400, the machine is fine. After that, machine is facing some issues. I can't say that. Each and every observation should be equally reliable. And these are called as line assumptions, which you should be aware of, which is very much important. Okay, see here, what is present next? Okay, that is fine. Now, here we are using or going to work on a specific data set called as empty cars or cars data set. Now here you have different input variables, that is volume. Volume is nothing but cubic feet of cab space, and horsepower, that is engine horsepower, and mileage, average miles per gallon, and top speed miles per hour, and weight, that is vehicle weight and hundreds of pounds. These happens to be your input. And what is your output here? Mileage is your output variable. Based on the remaining inputs, you will predict your output of mileage. Okay, now what? Now, our interest is to model the MPG of a car based on the other variables present. Now, what you do see here? There will be certain machine learning algorithms where you can't have any negative values. For example, the distance traveled. You have a concept called as distance travel. So distance travel that can't be negative. As we talked about distance measures that can't be negative, it will be always greater than or equal to 0. Now, or greater than 0. So the distance for that, such algorithms, it will not support negative values. You can't travel negative distance. In such kind of scenario, what people do is, they will force the fit to be, or the fit of the coefficient value to be starting from the origin itself. And one more key point to remember is, even if your intercept or coefficient value is even, it is statistically insignificant. You can proceed further with the model building. This specific scenario of taking this from the origin is called as zero intercept scenario. Zero intercept scenario. So let's see what is present here first. Then we will talk about it. So if you observe, we have to plot residuals versus predicted, errors versus predicted, residuals versus some of the independent variables. This is homoscedasticity. This is heteroscedasticity. What is homoscedasticity? What is heteroscedasticity? The variance, if you are not having constant variance, then that is hetero. If it is having constant variance, that is homo. This is what your chart is going to look like. How to fix this? This is what that is present in this particular module. Fine. Let's talk about some other things. Okay, so what is it? So one more important point you have to remember is, as I told before, if your intercept value is even, it is statistically insignificant. You can proceed further. In this data set, as we are using the methodology CRISP MLQ, the first we have to do is business understanding. Here the business problem is, what is the business problem? Significant number of customers are asking about the mileage of the vehicle, which is the output variable. Significant number of customers are asking about the mileage of the vehicle. If the mileage is high, then the sales will be high. If the mileage is less, then the sales are less. Assume this as your business problem. This is your business problem. Here, what is my objective? My objective is, I have to maximize the mileage. I have to maximize the mileage. And my business constraint here is the horsepower of the vehicle. The horsepower of the vehicle, it should not cross its significant threshold. That is my business constraint. That is, minimize my power and maximize the space in the car. All of these are constraints. Then you need to record the success criteria, the business success criteria, the ML success criteria, and economic success criteria. So what is this? So I will take the business success criteria as, you will end up helping in increasing the mileage of the vehicles by at least 30%. 30% increase in the mileage. And ML success criteria, I will probably build a model with an accuracy rate of 85%. And I have economic success criteria that I have to save a cost saving of at least $5 million. Suppose your data is in MySQL database. You have it in MySQL database. The customer of IT department will download the CSV file and he will share this data file with you. Once he shares the data with you, you take that data and proceed with the model building by using multiple linear regression, because we have multiple inputs and mileage is output variable, which is continuous. I have to use multiple linear regression. This is what happens in your real-time project. This is what happens in your real-time project. So what we have discussed in this particular module, we have seen what is dummy variable creation. When do you go for dummy variable creation? When When you have your output variable continuous and your input variable is single, and if it is discrete, then I will go for dummy variable creation. If I have output variable that is continuous and input variable I have multiple and these are discrete, then again I will go for dummy variable creation. And after that, I've talked about regression analysis. So in regression, you will have an equation y is equals to beta not beta 1 and so on. In multiple linear regression, you always have to understand the relationship between these coefficient values and the output variable, whether it is linear or not. And then we have also talked about when do we have to go for simple linear, when do you have to go for multiple linear. The next one that we have is logistic expression. Logistic is useful when we have the output variable that is categorical binary. This is what we are about to discuss. Let's see the mind map. What is present in the mind map? So here is our mind map. We are talking about baseline model. When I don't want to go for any model building, I can go for the baseline model. Here, this is built only based on intercept and no slope value. And the problems you have is heteroscedasticity. There is no constant variance. The transformation technique is the solution for this. And you have multiple linear regression. The continuous variable output is continuous. And you have multiple input variables. And you will build the model with complete data, test whether the p-value, test the overall p-value, test the r-square value, and the p-values are greater than 0.5, 0.05, then try to check and test for influential observations. And multi-collinearity, what is it? This is the variance inflation. Factor is a measure to determine on what variables are getting involved in collinearity. So added variable plots are used to determine these variables. So this is simple linear and also multiple linear. And next we will talk about the logistic expression or logistic regression, in which again you have simple and multiple. We will talk about it once we have our break. So let's go for a 10-minute break and come back. Okay, everybody, let's continue with the session. So we are done with the multiple linear regression. The next one that we have is logistic regression. So let's see what is present in the slide. So here, what we are talking about. So we are talking about the data mining concepts, within which what we are talking about supervised learning, and then in which we have classification techniques. And when do we apply classification techniques? When you need your output to be in categorical form. When do you apply classification techniques? When you need your result or output in discrete form or categorical form, you will go for classification technique. When your target variable is categorical, you need to apply classification techniques. Why? Because the return will be your categorical. This will return the outcome that is categorical. If I have a target variable that is numbered, I will go for regression techniques. As a part of this, we have learned the simple linear regression and multiple linear regression. Here we are applying linear regression techniques, which goes with the formula y is equals to mx plus c equation. This is predefined, which is already present, which basically talks about a straight line. Here we try to capture the linearity. The linear regression goes with which concepts? OLS concept, least squares, which we have already seen, which gives us coefficients which are slope and intercept here. For generalizing it for multiple equations, we write for the equation of straight line as y is equals to beta naught plus beta 1 into x1 plus beta 2 into x2 and so on. Depending upon the number of variables you have, we will have the number of coefficients in the equation. Now let's talk about the scenario when you have the output variable discrete. We can take classification like you have KNN algorithm, which is a distance-based algorithm in which you have KNN classifier as well as KNN regression. So you can take any algorithm designed to capture both numerical values as well as non-numerical values. Similarly, when we talk about regression, here also this is designed to capture only for continuous values. The variations that we have with respect to discrete data is what we are going to talk about. So regression analysis for discrete data. Let's see what is present in this module, the agenda. So the agenda for this module is the probability distribution. What is probability distribution? And what are the types of probability distribution? What is continuous probability distribution? And what is discrete probability distribution? And then what is logistic regression? That is simple logistic regression. And what is the use case? And what do you mean by confusion matrix? And what do you mean by ROC curve? We will see all these things in the module. So let's see the first one, that is probability distribution. So before talking about all these things, we have to first understand the distribution of our data. So before talking about all these things, we have to understand the distribution of your data. Now, when we are talking about discrete data, here also we will have patterns in the data. When we talk about continuous data, what is the default distribution? That is normal distribution. It is denoted with which notation? If I have a random variable which is equivalent to normal distribution, I can say this with the help of mean and standard deviation. This is my general notation. Now coming to the first one, probability distribution. So what is the use of probability distribution? Here, we will understand the spread in the data distribution. When you see the distribution of data distribution is more here, which is spread is very more here, which is understandable with the help of probability distribution. So see here what is present in the probability distribution. Why do we need to study this? To understand the spread of data. If we have fair idea of probabilities, we can use it for various analytics purpose. Now again, here you have two types. One is continuous probability distribution and second one is discrete probability distribution. Now, why we are understanding, what we are understanding about the spread of data distribution. So see here, if you observe this chart, the spread is very more here and spread is very less here. This is understandable with the help of the concept probability distribution. And within which you have two types, continuous and discrete. So types of probability distribution are continuous probability distribution and discrete probability distribution. So when we talk about this continuous probability distribution, here you have infinite number of possibilities or possible options like minus infinity to plus infinity. Now, if we can see the bell-shaped curve, the bell-shaped curve, which is normally talking about the normally distributed data. We don't have any abnormal cases. We don't have any abnormal cases, which means we don't have any outliers, which means if you don't have any outliers, you will see symmetric data. Coming to the discrete probability distribution, when we look at the number of cars in American households, see here, there will be an example provided here. So this is discrete and this is continuous. In continuous, you can see the bell-shaped curve. In discrete, this is not symmetrical. When we look at the number of cars in an American threshold, the number of cars is the discrete data. This graph shows in America, most of the cars or most of the people will not prefer using cars. So that is nothing but discrete probability distribution, which is not having any normally distributed data. These are the two types of probability distributions present. And see here, continuous probability distribution, there is an example provided. Height of adult males in the world. So maybe he is 1 feet, 2 feet, 3 feet, and so on. This is the probability. And what about the continuous? For continuous, that is the thing present, and discrete number of cars per household threshold, that is discrete data present on the x-axis and probability on y-axis. These are the simple examples. And coming to the next important thing, that is binomial distribution. What do you mean by binomial distribution? So this is one of the discrete probability distribution present. What is this binomial distribution? How can I understand this binomial distribution? A binomial random variable, see here, a binomial random variable. What do I mean by random variable? We already know about it. That is a variable which is having the number of successes represented by x in n number of repeated events. See here, a binomial random variable is the number of successes which is represented by x in n repeated trials of a binomial experiment. So what do you mean by a binomial experiment? A binomial experiment, for suppose we can take an example like flipping a coin. I am flipping a coin in which I have only either heads or tails as outputs, assuming I have only two options. So this is called as a binomial experiment, which is having only two outcomes. If you have a coin, if you are flipping a coin, if you flip it for 5 times, how many times? You are flipping it for 5 times. Now you are going to get heads. That is your success level. I want to get the success, which is heads. How many times you are going to win? That is something we are going to analyze here. So here, if I get heads, which means I win. If I get tails, that is I'm losing. When you flip a coin for 5 times, how many heads you will get? And number of times that we are talking about is called as a random variable. If you flip a coin, if you're flipping it for 5 times, so see here, there are how many possibilities present of getting heads? You may get 0 heads. All flipping 5 times, I will get 0, which is all tails only. I'll get 1 heads and remaining all tails only. I'll get 2 heads and remaining all tails only. 3 heads, 4 heads, and 5 heads. Any one of this will be the range of my outcome. We don't know how many times I will get head. It can be either 0 or 1 or 2 or 3 or 4 or 5. Randomly, it might vary. That is called as a random variable. If I ask others to randomly flip a coin for 5 times, so I got 3 heads. He may get 4 heads. So both our outcomes are different. Now, so what is the chance that you have that you get only 0 heads? What is the chance that you have you get only 0 heads? And what is the chance that you have you get only 1 head? What is the chance that you have that you get only 2 heads? Each one of the probability associated with it, I have to calculate. The probabilities that these values displace are called as binomial distribution. The probability distribution of this binomial random variable is called as binomial distribution. Let's say what is it? Let's say you have 5 chances. I am going to flip the coin for 5 times. Now, what may be the output? It may be 1, 2, 3, 4, and 5. Anything is possible. For suppose, check it out. For suppose, now, what I'm going to calculate? I'm going to calculate what is the probability that I got 0 heads. I have to measure that. And the only chance to get all zeros is if I get all tails. If I get all tails. So see here. In 5 flips, I got all tails only. no heads is present. Now I want to find out what is the chance or the probability associated with getting 0 heads. That is what I have to find. Now, what is the probability of each of it? You know there are only 2 outcomes here, heads or tails. So that is 50% probability for heads and 50% probability for tails. So what is the probability of tails here? There are only tails present. That is 0.5. And how many times? 5 times. This is the total probability associated with getting 0 heads. This is the total probability associated with 0 heads. Like I have a random variable. It may be the 0 heads, 1 head, 2 head, or so on. For 0 heads, what did I got the probability as? That is 0.5 whole power 5. Now, if I want to calculate the same thing, what is the chance of probability if I want to get the output as 1 head? What is it? See here. So, I have a random variable. I have here the random variable. It may be 0 heads. When I calculated the probability for it, I got it as 0.5 whole power 5. Now, what is the next question that I have? I want to find out the chance of probability of getting 1 head in 5 flips. So I got 1, 2, 3, 4, and 5 flips. And out of it, I have to get only 1 head. So in the first flip, I may get head. So remaining everything will be tail. In the second flip, I got head. So remaining everything will be tail. So just like that, I have to understand how many combinations are possible. We have to exactly get only 1 head in all the flips. And what is the condition or the combinations that I going to get? If you understand the question like NCR combinations, permutations, and combinations. So how can I understand the number of combinations? Here, the total number of flips are 5. And C, and what are the number of heads that I'm going to get? Only 1 head in this experiment. So what is the formula for NCR? NCR is equals to n factorial by n minus r factorial into r factorial. Now, based on this, I'm writing it for 5C1 and I will understand what is the output for that. So, 5C1, what is the output? 5 factorial divided by 5 minus 1 factorial into 1 factorial. So, I will write this as 5 into 4 factorial divided by 5 minus 1 is 4. So, 4 factorial into 1 factorial. Both will get cancelled out. So, I will get the output as 5. So, if I am going to just do the experiment for multiple flips in order to get 1 heads, the total number of combinations are 5 combinations. 5 options are there. Now I have to calculate the probability of every particular option present so that I will get the total probability of 1 head. Now how to calculate the probability? Let us calculate what is the probability of getting heads in the first trial and the probability of remaining else we will calculate. So what is the probability of head? Only 1 is present, that is 0.550%. And what is the probability of the others? 0.5 present for 4 times. I have 5 options like this. So what is the probability of getting 1 head? 5 into 0.5 into 0.5 whole power 4. This is my probability of getting 1 head in my experiment. Now you have to do it for multiple things, for getting 2 heads, for getting 3 heads, for getting 4 heads, and so on. Let's calculate one more time. See here. Now, for getting 0 head, the probability is 0.5 whole power 5. For getting 1 head, the probability is 5 into 0.5 into 0.5 whole power 4. Now what? I want to find out the chance or probability to get 2 heads in my experiment. Total number of events are 5 flips and I have to get 2. So how many number of combinations? N, C, R. So N is 5, R is 2. So what is the formula? 5 factorial divided by 5 minus 2 factorial into 2 factorial. Now how to write it? 5 into 4 into 3 factorial divided by 3 factorial into 2 factorial, which means 2 into 1. So 3 factorial gets cancelled. 2 2s are 4. So totally, if I want to get 2 heads in 5 flips, I have 10 combinations present. Now how to calculate it? See here, 1, 2, 3, 4, 5 flips are present. Now, if I have to get 2 heads, the starting 2 will be heads, remaining all tails. Or The middle two will be heads, remaining all tails. So you will have a lot of experiments. Now, what is the probability of getting heads here? 0.5 whole square. And what is the probability of getting tails here? 0.5 whole cube. How many chances or options are there? 10. So for getting two heads, what is the probability? 10 into 0.5 whole square into 0.5 whole cube. This is the probability for getting two heads in 5 flips. This is my calculation for exactly two success, that is two heads in our scenario. I can generalize this particular formula. How can I generalize this? See here. How can I generalize this formula? So if I have 5C2, I got the probability that is 0.5 of n success. Let us call the probability of success as P. So how many success we have? P square. P square. If the probability is, if P is the probability of success, so what is the failure? That is 1 minus P. So how can I write it? So P square of T, what can I write it as? 5C2. If I have 5C2 experiments, P square into, here, P is nothing but the probability of success. And this is the failure, that is 1 minus P whole power cube. How did you get the cube? That is 5 minus 2. And out of which 5 are the number, total number, and 5 minus 2 are the success. Sorry, this 2 is the success and 5 minus 2 is the failure. Now, how to get the generalized equation for that? NCR into P power, NCX into P power X into Q power N minus X. P is the success, Q is the failure, N is the total number of events, and X is the success that you want. So this is the formula for your binomial distribution. See it here, what is present here. This is the formula for your binomial expression or binomial distribution. This is the formula. So now, if I want to calculate for 3 heads, what is the formula? That is 5C3. What is 5C3? 5 factorial divided by 5 minus 3 factorial into 3 factorial. 5 into 3 into 2 factorial divided by 2 factorial into 3 into 2 into 1. Cancel, cancel. Oh, here you did not write 4, no? Into 4 also. So 3 gets cancelled. 2 2s are 4 again. And how many number of calculations are there? 10. So there are totally 10 number of options that we can choose. Now, based on the based on the formula, how can I get it? If I have 5 flips, how to know the probability of getting 3 hits? Now, what is it? Here, the success is 3, 5C3. Now, just modify the formula according to that. 5C3 into PQ and 1 minus P again, you can write it as Q power 5 minus 3 square. This is what your formula looks like. If I have, this is what your formula looks like. Now let's see what is present in the slide. Probability associated with the outcome, number of trials, number of success decides. See here. N is the number of trials, successes are X, and P and Q are the probabilities associated with the success and failure. This is your formula. Now what? If you have a normal flip coin, that will be your formula. You have a fudged coin as well. Check it out. So if you have P and Q 0.5, N is equal to 5, X is equal to 3, this will be your format. And if you are having a fudged coin, if I have a fudged coin, P and Q will get impacted. If the probability of success is high or increasing, what is the probability like? The more number of flips you do, the more heads you will get. So see, the probability distribution is somewhat different. If the probability of success is less, then it becomes right skew data. What is it? If the probability or the success is less, then it becomes right skew. If the number of flips are more, then more heads you are getting. The success is very high, then you will get left skew data. This is what the data distribution changes when you have a fudged coin and a normal coin. Now, you have the next thing, that is expected value. Check it out. The next one that we have is expected value. What do you mean by expected value? Expected value is nothing but the weighted average. What is this? Expected value is nothing but the weighted average. We already talked about this before. So this is nothing but weighted average. Now, What is the formula of expected value? So see here is the formula. This is your formula. Mu is equals to NP. What is the general formula? How will we write the expected value? Expected value is equals to sigma every random variable into probability of that variable. This is your formula. That is written here as mu is equals to NP. In binomial distribution, the expected value is NP for a fair coin and for a fudge coin. Okay, this is what you have the expected value. The next concept, let's see the use case present. See here the fudge coin as well as for a fair coin. The binomial distribution for the expected value is same. Okay, and coming to the use case, let's talk about the use case for binomial distribution. So see here, we have a trainee machinist. He is working on a lathe making dowel pins. It is a machine which is making dowel pins. There are only two dimensions present. What are the two dimensions here? That is, one is length and second one is diameter. Based on his past experience, he says that he is making 20% defectives. We are defining these defectives here based on two dimensions, that is length and diameter. If this dowel pins width increases, then what happens? If the size is increasing, then it will not fit within the gaps. If that size is too small, it will not stay there. It falls. And coming to the diameter is also one of the crucial one in manufacturing these pins. So here, length and diameter are the two things that we have to concentrate on which the defectives are mostly focusing on. When we are assessing the trainee machinist, we observe there are 20% defectives present with respect to length and diameter. Now, a quality control engineer, he is accessing the work of that particular person. Now, what is the probability that I will get exactly 2 pins as defectives? Now, observe the question. Exactly 2 pins, he want to get it as effectives out of 5 pins. How to calculate? You already know about this. That is, total number of events is 5. And the success rate that I want to get, that is X is nothing but 2. I have to find out the probability of success and probability of failure. Now, the combinations, how many are possible? NCX, that is 5C2. What is 5C2? You have to calculate. Now, what is the success and what is the failure? Success is nothing but this particular thing that is already given 20%, that is 0.2. And coming to the failure, Q is equals to 1 minus P. That is 1 minus 20%, 0.2, you will get it as 0.8. So the P is 0.2 and Q is 0.8. Now what is the formula? NCX into P power X into Q power N minus X. So 5C2. P power X is, P is nothing but 0.2, 0.2 whole square into Q is 0.8, 0.8 into 5 minus 2 cube, whole cube. This is my output for binomial distribution based on my formula for this particular question. This is basically what you have. It is Wright's cube data. Check it out what is present here. This is the pin. What is the success event? 0.20, 0.85 and 2. Now this is Wright's cube data. Now you have another question or another use case given for you. The second example, here we are looking at the telemarketers. Imagine you are the manager and you are assessing the performance of 2 persons. One is Steve and the other one is Wilma. Now Steve makes 10 calls per day. Whereas Wilma, he will make only 14 calls per day. Now, the success rate of this particular Steve is 80%. And here the success rate is only 45%. Now, if you have the question like who is performing better out of 2? Now, you can say based on the success, Steve is performing better. But in order to understand about this clearly, you have to set a target. Here, what is the target? We have to set the target and we have to observe their performance. We are comparing here the 6 sales per day for both of the people. Now we have these values and we will have to find out the overall calculation. What is the values that we have? Steve and Wilma. The total N values is nothing but I have 10 calls per day and 14 calls per day. Now the X value, what I want to find out, 6 sales. So 6 sales and 6 sales. And the P success criteria 80% is 0.8. P is 0.8. And here 0.45. And coming to Q, Q is nothing but 1.1 minus P, that is 0.2 and 0.55. These are the values that we have. Now, what is the formula for calculating the overall? NCX into P power X into Q power N minus X. Now, how to calculate this? First, we are about to calculate for Steve. For Steve, these are the values. So what is N? 10 is N. 10CX is 6. 10C6 into 0.8 whole power X, that is 6, into 0.2 whole power 10 minus 6, that is 4. This is what I have for Steve. And what about Wilma? What about Wilma? So Wilma is N, that is 14. 14C6 into 0.45 whole power 6 into 0.55 whole power 8, because 14 minus 6 is 8. So these are the two calculations. Now we will talk about the next thing, that is logistic calculation. Based on this, we will measure the performance. Fine, this is done. The example of binomial distribution is done. Now, we will talk about the logistic distribution. One of the variants of regression techniques which we will try to understand here is logistic regression, in which you have again simple and multiple. When do you use simple and when do you use multiple? That you have to understand. So, simple logistic regression is where you have an independent variable which allows us to try and predict the output variable. You have one independent variable, you are trying to predict an output variable. And here you have multiple input variables, x1, x2, x3, and which allows us to predict the output variable. This is where I will use multiple logistic regression. Now, how does logistic regression works? It will work when your output variable is categorical binary. It will work when your output variable is categorical binary. When we say binary, you already know it is having only zeros and ones, or yes or true, yes or no, or true or false. Only two cases are present. Now, regression is a statistical based algorithm. Now, logistic regression is nothing but it talks about the probability that your output variable is 1. And the probability values lies in the range between 0 to 1. How does this probability actually work? Suppose you are writing an example. You score marks. How your marks will be? It will be maybe 0% to 100%. So, what I need here is whether a student is passing the exam or failing the exam. How do we declare whether a person or a student passed or not? Based on the concept called as cutoff. You already know, out of 100 marks, if I get more than 35, then I am passing the exam. If not, that student is failing. Now, this is not the case in every scenario. In logistic regression, we predict the probability associated with the outcome. So, probability of pass, that is nothing but the true event or successful event. I will represent it as 0. And probability of fail, that is nothing but 1 minus P. We call it as failure event. We also represent is that 0. This is 1 and this is 0. Now what? Now what is present in logistic regression? Let's see what is present in the slides. A simple independent variable model is called as a logistic simple regression. Multiple independent variable model is called as multiple logistic regression. So logistic regression model predicts the probability associated with each dependent variable category. How does it do this? How we can do this? So here, it finds the linear relationship between independent variables and the link function. What is it? It finds the linear relationship between independent variable and the link function. Then the link function provides the best goodness of it. So before talking about that, we will see here. What is that? In a data set, you have multiple variables. Like you have one output variable, which is binary, that is 0, 1, 0, 1, everything will be zeros and ones. We are predicting what is the chance of the student passing the exam. If we want to do like this, if y is equals to 1, he will fail the exam. If the output variable is 0, he have to pass the exam. If I want to do the interpretations in this manner, how to do it? Based on the concept called as cutoff, which we already told. If the probability of y is equals to 1, is greater than the cutoff, then we predict it as 1. 1 means what? He is failing the exam. If the probability of y is equals to 1 or less than or equal to cutoff, I'll predict it as 0. 0 means passing the exam. This is what we have understood about the cutoff concept. So here, if the probability of y is equals to 1 less than or equal to cutoff, we predict it as 0. The important question here is, what is the cutoff value? What should be the cutoff? So linear regression, the possible outcome that we are looking at will be in between minus infinity to plus infinity. When we talk about the logistic regression, the output variable is either 0 or 1. And the graph that you are seeing here will be a S-shaped curve. See here, there will be a graph. So this is a simple linear regression, but when we are observing logistic regression, it is an S-shaped curve, that is sigmoid curve. What is this called? This is called as a sigmoid curve. So here in logistic regression, we will take the default cutoff as 0.5. So multiple logistic regression is nothing but the relationship between the parameters and the output variables are changing. If I use the equation, see here. If I use this equation, I will get a continuous output. What we do? See, understand everybody? So this is our equation. If I use this equation, I will get a continuous output. What we do is, we will substitute the continuous output into probability function. What is the equation of probability function? P is equals to e power. So see here. P is equals to e power y by 1 plus e power y. You have to just understand this particular formula. This is probability function. So we will apply the continuous variable output into this link function or probability function. We have different variants in logistic regression. What are those? Binary logistic regression, and so on. So see here. The variants of logistic regression methods include, first one is binary. What is binary? What is nominal and what is ordinal? Now, binary logistic regression is if you have two categories present in your data. Example is presence or absence of a disease. Then that particular variant is called as binary logistic regression. What is this called? This is called as binary logistic regression. Now, if you are having greater than two categories, your value will be either nominal or ordinal. Nominal means all the categories are equally important. In this case, the technique that we are going to apply is called as multinomial regression. In this scenario where I'm having nominal data, which is categorical, in which I have to equally take the importance of every category present, the technique that I'm going to apply is called as multinomial regression. If your data is ordinal means you will have a rank. Then the technique that we are going to apply is called as ordinal logistic regression. These are the variants present. And we have also talked about the assumptions present. What are the line assumptions that we have discussed? So, okay, before talking about the assumptions in logistic regression, we will have a quick reminder of what we have discussed about linear regression. So you have line assumptions present. What do you mean by line assumptions? What does L stands for? L stands for linearity. In line assumptions, L stands for linearity. In linearity, what is that? When we talk about linearity, we have to check whether the output variable and input variable are being linear. Whether the output variable and the coefficients or parameters are linear. Whether the input variable and input variables are being non-linear. We have to check all these things. If these two are linear, then what is the problem that you're going to encounter? That is collinearity. If you are having two input variables in normal, then we will encounter the problem called as collinearity problem. That stands for L. Now, what is I? I stands for independent. I stands for independent. What do you mean by independent? When we talk about independent, we say that errors should be independent of each other. What if the condition does not satisfy? I will get the condition called as autocorrelation problem. I will have autocorrelation problem. Now, what is N? N stands for? N stands for normality. Errors should be normally distributed. Errors should be normally distributed and average of errors should be equal to 0. If not, we will have a biased model. And what does E? E stands for equal variance. E stands for equal variance. Now, what is equal variance? Error should be constant. If you are not constant, then we will get a problem called as heteroskedasticity. These are the things that we have discussed in linear regression, the assumptions. Similarly, you have some assumptions for logistic as well. What are those assumptions? See here. The first property talks about only one outcome per event. Imagine you have, event, imagine it as a record. For each record, you will have one outcome. That is your first assumption. And the second one is the outcomes are statistically independent. One outcome should not influence the other one. They should be independent of each other. And all relevant predictors are in the model. Predictors are nothing but the input variables that you are going to choose in order to predict your outcome or output. When you are trying to predict, here one category at a time. When you are trying to predict, they should be mutually exclusive as well as collectively exhaustive. What do you mean by that? If I want to predict whether a student is passed the exam or fail, which means I don't have any other particular thing, only pass or fail is present. So here, if a person is passing the exam, which means he is not failing it. So these are mutually exclusive. If one occurred, the other thing will not occur. And these are mutually exclusive because there is no other thing that comes apart from these three. So one category at a time, they are mutually exclusive and collectively exhaustive. Sample sizes are larger than the linear regression. So this is what present here. These are the assumptions present in logistic regression. And coming to the simple logistic regression, when do you go for simple logistic? When you have output variable discrete and the inputs are only single and continuous, you will go for simple logistic. When you have discrete output variable and the input variable is single and discrete, you will go for dummy variable creation. That is simple logistic regression. And here is your use case. You can go through the use case. We'll talk about it in the next session. So for now, what we have understood up to now, we will talk about this use case in the next session, the logistic expression. Now, what did we understand up to now? What did we discuss up to now? So we have discussed about the supervised machine learning algorithms. Unsupervised is completed. Unsupervised, within which I've told you, hierarchical, in which agglomerative, and non-hierarchical clustering, in which k-means is there. And also we have discussed about the next thing, which is used to overcome the drawbacks that is present in k-means algorithm, that is db-scan. That is density based. And the next one we have seen is association rules. This is unsupervised. And coming to the predictive modeling, that is supervised machine learning algorithms, you have here different algorithms which we have seen naive Bayes. And the second one is KNN. This is based on nearest distance. And the third one is decision tree. And the fourth one we have seen is regression. Okay, we are done with all these things and we have also seen how to do it in RapidMiner Studio as well. This is the operator naive Bayes. And KNN, what is the operator present? That is KNN. And decision tree is there. And linear regression is that. And what is it? So these are supervised machine learning algorithms. When you are applying this in your RapidMiner Studio, you have to remember you have to split your data. Split your data into training data set and testing data set. In training data set, you have to apply your machine learning algorithm. After that, based on the accuracy, you have to go for which type of method you want to choose. And in order to split your data, there are two operators present in RapidMiner Studio. One is split data and second one is cross-validation. In order to customize every operator you have to use the parameters component present. the parameters component present. Now what else? Now what else are there? So here, okay, decision tree. What did we discuss about decision tree? Decision tree we have here, which is having three different types of nodes. What is that? That is root node, internal nodes or branch nodes, and then the leaf node. Based on the nodes, based on the greedy algorithm, based on entropy, based on information gain, the ultimate thing, we will decide which node or which column needs to be the root node. So information gain, what is that? That is entropy before minus entropy after. And entropy is nothing but the measure of impurity. And here, accuracy is there, which is the measure of purity, which is 1 minus entropy. And entropy after, how to calculate it? It is calculated by calculating entropy on the right-hand side, on entropy on the left-hand side. By calculating this, I will get the information gain. Based on this, I will choose which of it I have to choose it as the root node. And the next one that we have is regression models. And regression models, you have again linear regression and logistic regression. And linear regression is used when you have your output variable is continuous. When you have your output variable discrete, you have to go for logistic regression. And in linear regression, again, you have to simple linear regression and then multiple linear regression. And simple linear regression, when do you have to use this? When you have your output variable continuous and only one input variable is there. If it is continuous, you can directly use this. If it is discrete, you have to go for dummy variable creation. That is nothing but simple linear regression. What do you mean by multiple linear regression? It is used when you have output variable that is continuous and when you are having multiple inputs. And these inputs are continuous, then I can directly apply the algorithm multiple linear regression. If it is discrete, then again I have to go for dummy variable creation. And you already know about regression. In regression, you have the concept called as y is equals to beta naught and something, the formula. This is in the form of a linear expression. And we have also discussed about scatter diagram. And coming to the logistic regression. The logistic regression, when do you use this? When we have the output variable that is continuous, that is categorical binary, which means discrete. Now what? Now here, in this again, we have two. Simple logistic and then multiple logistic. And when do you go for simple logistic regression? When you have your output variable discrete categorical, which is binary data, and your input variable, single input variable that is continuous, I can directly use my simple logistic regression. If the input variable is single and it is discrete, then I have to do the dummy variable creation and I have to apply this method. If my output variable is categorical binary and I have multiple inputs which are continuous, I can directly go for multiple linear regression. But if I have output variable categorical binary and inputs are multiple which are discrete again, I have to do the dummy variable creation, which is based on that I will apply the algorithm multiple logistic regression. This is what we have seen, and we will discuss about the use case of logistic regression. And in the next session, we will talk how to apply those things and how to work on it in RapidMiner Studio. So I hope this session is helpful for you. We will meet again in the next week, which is on Friday at 10 a.m. So thank you so much.